Hello, everyone. Thanks for watching this video. Today I'm going to talk about our work CFGR, Coarse-to-Fine Gaze Redirection with Numerical and Pictorial Guidance. Gaze redirection aims at manipulating the gaze of a given face image with respect to a desired direction, a numerical reference angle for instance, and it can be applied to many real-life scenarios, such as video conferencing or taking group photos. However, previous work on this topic suffers from low-quality image generation and low redirection precision. In this paper, we propose to alleviate these problems by means of a novel gaze redirection framework which exploits both a numerical and a pictorial direction guidance, jointly with a coarse-to-fine learning strategy. The contributions of our work can be summarized as follows. 1. A coarse-to-fine eye gaze redirection model which combines flow learning and adversarial learning. 2. An NPG module which integrates the pictorial gaze map with numerical angles to guide the generation process. I'd like to illustrate the details of our model next. As mentioned before, our model can be roughly divided into two branches. The coarse branch learns the spatial transformation which warps input image according to desired gaze, and the fine-grained branch reduces the gap between the previously warped image and the ground truth image and recovers finer texture details. I'd like to clarify the notations adopted in our slides and paper then. We use X to represent a RGB image and R represent a numerical angle vector, subscript A, B representing source domain A and target domain B. The lowercase h represents head pose. The delta R subscript uppercase S represents our numerical and pictorial guidance module, which is referred as NPG, would be depicted later. The coarse-grained branch adopts an encoder-decoder architecture. Specifically, encoder takes X subscript O and its corresponding head pose H as inputs. Then, decoder generates output using both the encoded code and delta R subscript S provided by NPG module. Note the conditional information delta R subscript S is concatenated into different scales of decoder to strengthen the guided ability. The output of decoder is a two-channel map, rather than an image, which is used to warp the input image X subscript A by means of a bilinear sampler BS. We only use L2 distance between the output and ground truth as the objective function of coarse-grained branch. Before we go into the fine-grained branch of CFGR, I'd like to talk about the NPG module first. It can be seen from the slides that the output of our NPG module consists of three parts: an angle vector difference delta R, which computed by the difference of R subscript A and R subscript B, and two pictorial gaze maps generated by corresponding angle information. Next, I will detail how we generate the gaze map. As shown in the slides, our gaze map is a two-channel Boolean image. One channel is for the eyeball, which is assumed to be a perfect sphere, and the other channel is for the iris, which is assumed to be a perfect circle. For an output map of size m times n, with the projected eyeball diameter 2k equals 1.2 n, the coordinates micro, nu of the iris center can be computed by formulations in the slides. The theta and pi in formulation means two dimension of r, yaw and pitch, respectively. More details can be found in our paper. Note that the synthesized gaze map only represents the gaze angle, without identity details of the specific eye sample. We provide more visual examples of gaze map for better illustrating. Now, I'm going to talk about the designed multitask condition GON network in our fine-grained branch, which is essential in generating realistic images. Instead of manipulating the whole image directly, the model learns the corresponding residual image defined as the difference between the coarse output and the ground truth. We use uppercase R to represent the learned image. Under multiple conditional information, the generator is optimized by the L2 loss and perceptual loss. More details can be found in our paper. Moreover, we use a multitask discriminator which performs adversarial learning and regresses the gaze angle simultaneously. So far, I hope I have given enough information about our model architecture, and I prefer to show the performance of our model briefly as follows. I'll start with qualitative comparison. We compare the proposed model with two baselines deep warp and PRGAN, and we refer to the coarse-grained branch as CGR. The zoom-out results is shown in the last row. It can be seen that our full model outperforms baselines, not only in texture and shape but also in redirection precision. Next, we plot the gaze estimation errors and LPIPS scores of baselines. We split problem setting according to head pose, and the angle difference between source and target domain. It can be seen that our model achieves better performance in most cases. Moreover, we present much more experiments in our full paper, including ablation study. We recommend to read the paper for more experiments results. That's it. Thank you for listening.